Okay, in this video lesson, we're going to talk about how we can use the size of an atom to predict two more trends. And in particular, we're going to focus just in this one on ionization energy, or the energy required to remove an electron from an atom. Okay? We already know if you give an atom energy, we can make those electrons jump to higher energy levels, and then they fall back down and they emit light. We've learned that before. But what happens if we give them enough energy that when they jump, they leave? Okay? Well, if you give them enough energy and they jump up and they don't come back, could they leave the actual atom? That's called the ionization energy. It's the energy it takes to ionize or to remove an electron from an atom. Okay. So one major concept we have to have down before we can move forward is reminding ourselves that the smaller the atom, the stronger the electrostatic attraction. Okay. So those electrons are held by the nucleus. And the smaller that atom is, the tighter they hold those and the better they hold on to those electrons. Okay? So knowing that, would we expect big atoms to hold on to electrons, their outer ones, really well? Or would we expect small atoms to hold on to their outer electrons really well? Well, hopefully you're thinking that the small ones hold on better, and the big ones don't do as good a job. In that case, that would mean that the size that would require the least amount of energy to remove an electron was probably going to be the biggest atoms out there, okay? And that's what we actually see. So if we take a look at our trend here, we're not going to look at the details yet, but just generally speaking, we have smallest atoms here and biggest atoms here, right? The atomic numbers here, and this is ionization energy. If you look, the general trend, if we drew one line for all of this, would so have it sweeping down this direction, which means the bigger something gets, the less energy it takes to remove an electron, okay? So your biggest atoms take the least. Your smallest ones take the most, which means in the bottom left-hand side of our periodic table, that takes the least amount of energy. In the top right, it takes the most amount of energy, okay? Now, let's take a look at each individual period and group to see how that plays out. So here we have, let's start here with sodium. Sodium is an alkali metal, it's group 1. And we move our way up to argon is in group 18, okay? So this represents going across the periodic table from sodium to argon. Here we see potassium going to krypton across the periodic table. So each bottom point to top point represents one period across the table. Here we see a trend that from potassium, which is the biggest element in period 4, as you move across period 4 to zinc, to gallium, to krypton, which is the smallest element in period 4, the amount of energy it takes actually increases, which also makes sense in our trend because this is the smallest, it should take the most energy to remove an electron from it. This is the biggest, it should take the least amount of energy. And that repeats itself over and over again. Sodium to argon, rubidium to xenon, cesium to radon. It always shows that. If we look just purely going down a group, so what about just the alkali metals themselves? Well, lithium to sodium to potassium to rubidium to cesium to francium, they all are pretty low, but lithium takes the most, francium takes the least, because francium's the biggest, lithium is the smallest of those. So again, we're reinforcing that idea that the smaller the atom, the more energy it takes to remove an electron. The bigger an atom, the less energy it takes to remove an electron. Now, are there any discrepancies? Oh yeah, all sorts of those. So let's talk about discrepancies, okay? So why do discrepancies happen? It has to do with stability, okay? And because we know electron configurations, we know there are certain elements on the periodic table based off of where we put the electrons that they can be more stable than others. So we know that when you fill an orbital, or you half fill an orbital, or if you completely fill an energy level, like the noble gases do, that plays a role in how stable they are. Well, the more stable an element is, the harder it is to remove an electron from it also, okay? So their size and stability are the two things. So let's look at group 18. Group 18 is tiny. They are the smallest elements in their period, and they're super stable. So for group 18, it would make sense that they have all the peaks. They're the highest ionization energy. Look at group 1, our alkali metals. They're the biggest elements in their period, and they're the most unstable. So it makes sense that they should have low ionization energies, okay? But what about right here, like zinc, cadmium, and mercury? Well, if you remember, those are all group 12 elements. And if you recall, group 12 is where the d orbital fills. So when you fill the d orbital, you are now backfilling an orbital from a previous energy level, which creates another really stable configuration. So they're not smaller, bigger than the things around them. They're just way more stable. Okay, so zinc, cadmium, and mercury, they're a more stable element within their particular groups. So because of that, they're abnormally stable. Okay, that breaks our trend where we see this kind of spike, where they actually get a much harder or much higher ionization energy. Now, the exact opposite is true if we take a look at group 13. Group 13 is things like boron, aluminum, gallium, indium, thallium. They're all elements that have one electron in a p-shaped orbital. So they are more unstable than the things around them because of that single electron in that p orbital. So as a result, they're abnormally unstable. That also breaks our trend, so we see them drop down. So you see a spike at zinc and a big drop at gallium, a spike at cadmium and a drop at indium, a spike at mercury, a drop at thallium, because super stable, super unstable in comparison to their size around them. Every little blip on here has some sort of reason behind it. It has to do with stability, okay? You're responsible only for the groups 12, 13 kind of juncture, because that's the most obvious one that we see, okay? And obviously you're responsible for the general trend of going across the table or down it as we go, all right? Now, what should happen to the size of an atom when an electron is removed, okay? So if we take one electron away, we give enough energy that things leaves, it ionizes, and we take the electron away, would the atom get bigger, or would it get smaller, or stay the same? Hopefully your intuition says it's going to get smaller, because it does, okay? Let's take a look. This is the pink spheres or red spheres are all the atoms. The blue ones are all the ions. In every case, you compare the red to the blue is smaller, okay? Let's talk about why, okay? If we take an electron away, two things are going on. One, sometimes we're emptying an orbital. So if you empty an orbital, it's no longer there. That would make it smaller. That's kind of a no-brainer, okay? But a lot of times when we ionize, we don't empty orbitals. Like, for example, titanium taking 2 away, that would empty the d orbital. But manganese taking 2 away doesn't empty the d orbital for them. The d orbital still exists. They're just somewhere in the middle of that, okay? So why does it get significantly smaller? It doesn't have to do with emptying out orbitals. It has to do with the difference of the electrostatic attraction, okay? So if you are an atom, and let's say you have 20 protons in you, and you have 20 electrons in you, okay, there's 1 proton for every 1 electron. So there's a balance of electrostatic attraction, okay? Now, let's remove 1 electron from that scenario. So now you're down to 19 electrons. Well, you still have 20 protons. So you still have 20 positive particles pulling and holding on to the remaining 19 electrons. So each electron doesn't feel the pull from 1 proton now. It feels the pull from 1 proton plus a portion of the proton that doesn't have an electron anymore, okay? Now, they don't pair up like that, but the idea is that way, okay? What if you remove 2 electrons? So, for example, like iron, it removes 2 electrons or even 3 electrons, okay? So for iron, it starts off having 25 protons and 25 electrons. Well, if you take away 3 electrons from that, now there's still 25 protons pulling and trying to squish the electrons as tight as possible, but there's only 22 electrons that are flying around trying to get away. So now the pull from those 25 kind of overpowers the 22 and it shrinks them down even smaller, okay? So the result of this is every time you take an electron away, your atom gets smaller, okay? So all of our cations, or our positive ions, are always smaller than our atoms. Now, what happens because of that? Well, is there some sort of relationship between how many electrons are removed and what goes on? Yep. It has to do with size and stabilities too. Okay, so let's do a couple recalls here. Each ionization and removal electron will make the atom smaller. Okay, so as you take more electrons away, they get smaller. Okay, so if they keep getting smaller, is it going to be harder or easier to take more away? Let me give you an analogy. If you had a bag of chips and I asked to take 1 chip from you, you'd probably be like, okay, Mr. D, you can have a chip. Okay, but if I asked for a second chip or a third chip or a fourth chip, wouldn't it get harder and harder for you to give away your chips because at some point you're running out and you're going to hold them tighter and tighter and tighter. Same thing here, but it has to do with size, where the smaller it gets, it holds onto those electrons better. So every time you remove an electron, it gets harder. It takes more energy, okay? There is a limit to how many electrons can be removed from every atom. That limit has to do with stability. So where do they hit stable points inside of their structure, okay? So let's talk about those stable points. We take a look here. We have sodium, magnesium, and aluminum. For sodium, taking one electron away would make it stable like neon. For magnesium, taking 2 electrons away would make it stable like neon. For aluminum, taking 3 electrons, 1 from the P and 2 from the S, would make it stable like neon, okay? So the noble gas configuration is one way that we can kind of visualize the stopping points, all right? Look at the energy amounts. To take 1 electron away for sodium, very little energy. But to go past that, so if you took a second electron from here, which means you're trying to break into neon's configuration, would be super high. Notice how for magnesium, the amount of energy it takes to take 2 electrons, not very much. But to take 3 is extremely high. For aluminum, the amount of electrons, energy for 3 electrons, not bad. But for 4, really, really high. In fact, it takes less energy, let's say, for magnesium to take 2 electrons away than it does for sodium, okay? They're both taking 2 electrons away, but magnesium is way easier than sodium. Well, that's because magnesium has 2 electrons in an unstable way, where sodium only has 1, so it will not let you take that second electron away, okay? So where does our limit lie? Well, it lies with stability, okay? Once you hit a stable configuration, it takes more energy to remove those electrons, all right? So that same configuration as a noble gas, the D block can also be full, included with that. The ions start to get too small, and the energy required to remove the electrons is too high to continue. That's our limit, okay? That's why we say sodium could only ionize to be a 1+, and magnesium could only be a 2+, and aluminum is going to be a 3+. They can't go past that point because they now have too much energy required to take another electron away in a normal situation or in a natural world, okay? But up until that point, they can do that, all right? So for sodium, 1 ionization is allowed. For magnesium, 2 ionizations are allowed, and aluminum, 3 ionizations are allowed. That same pattern plays itself out for every element on the periodic table. That's every metal. They're allowed to ionize until they've reached a stable configuration of some sort, and that's their limit, okay? And the reason why is because it just takes too much energy. They're too small, because they keep getting smaller, and they become stable, and they won't ionize past a stability point, okay? That's how it kind of works. Now, that is our different things of our ionization energy. So we want to take a minute just to review and make sure we got it down. First of all, general trend, okay? Ionization energy is the amount of energy it takes to remove an electron. So the bigger you are, the less it takes. The smaller you are, the more it takes. The more stable you are, the more it takes. The less stable you are, the less it takes. So it's a combination of stability and size, okay? Is there a limit to how many electrons can be taken away? Yes. That limit comes from stability. So you can keep removing electrons, even though it does take more and more energy, until you get to a point where you have a stable configuration, and then the jump in energy is going to be too much to allow it to ionize past that point, okay? So our general trend follows basically about size. Stability deals with all those discrepancies and endpoints and kind of like where does it get to be too much, those kind of things. Last idea, remember, every time you ionize, it gets smaller. So if it gets smaller, it always takes more energy to take another electron. So taking 1 away is always going to be easier than taking 2 away, taking 3 away, and so forth. All right, that's it, my friends.